Greetings and welcome to another C# coding session. We are working on a Minecraft server launcher with restart options, daily backup options, stuff like that. And last time we started adding in some extra stuff for custom colored texts, say for in-game chat warnings before the server shuts down, things like being able to customize how the message of the day looks. Actually, I'm going to showcase that quick. I have had a super busy week, so I do have to admit I'm a little bit unprepared today. Bear with me, please. Okay, so this would be a screenshot from the game client showing if it's, there we go, showing Applecraft and my own little local server. The reason I want to showcase this is to give an example of what can actually be done with the customized MOTD within the server properties configuration. Now, as you can see, Applecraft has 2 lines of information, and part of it is looking like a rainbow of colors. This is stuff that is perfectly doable with the chat converter stuff that we created last time. We have a foundation to be able to do something similar for our setup. The custom text dialog that we started doing a little bit on last time will hopefully end up becoming a nice way of editing these texts so we can see what they potentially will look like when deployed into the configuration files and such. Another thing I wanted to showcase was I did a little bit of capturing. Christ, I just installed those updates. Thank you, Microsoft. I've been installing updates all morning. Anyway, so here I have cut out a section of let's see the other one. Yeah, here we go. I've cut out a section of the multiplayer listing just to kind of give an idea of how big these profiles actually are in the game client. And the reason that it's showing the same text twice is because the first one, the white one, is the text that I entered when I added the server profile to the game client's listing. And the second one is the one that comes from the actual MOTD. So what I find interesting about this is that we can actually measure exactly how many pixels we have available to write the text on. So if we take a look at this one again, it's pretty much the same thing, but here we've got the double-lined MOTD message set up. And we also have a couple of extra icons here to indicate whether the client is compatible with the server. If it's pure vanilla and modded, get a different icon and so on. Excuse me. Um, and this particular listing does give us some measure of how big we can do this in terms of editing those custom texts. So last time we also had a look at the built-in, let's see, default font, which would be this one. And we talked about building up something that would be able to effectively render an image containing the text based on this glyph template. While going through the entire UI of our server launcher just before starting the stream today, I kind of got the idea that I should probably consider doing a UI change of some kind to kind of consolidate where stuff is. It can be a little bit how should I put this, messy, trying to figure out where stuff is and how we configure it, and the schedule stuff, and if we're putting in custom warning messages for restarts and backup shutdowns. We might want to do well, I guess come up with some kind of facelift for the entire UI, since at the moment this is the core configuration of each server profile, and that then pops the server properties changes where the message of the day is, which means we would have yet another dialog on top of this one for the custom text editing. So that could easily become a little bit messy. In a similar fashion, the schedule stuff is here, which is kind of separated from the rest of the configuration. So I guess it would probably be a good idea if we can come up with some better way of organizing the entire UI for all of this miscellaneous configuration and handling. Well, let's get this closed down. So for the current UI rendering, I basically just picked a random size that seemed to fit at the time. And basically just added in all the handling stuff for it to kind of make it fit. We could, of course, just for the sake of argument, we could attempt to see if we could build or rebuild our UI to basically simulate what the game client looks like. Alternatively, just add in some UI updates, making use of this glyph-based rendering stuff instead. Plenty of different ways that we can go about this. In any case, we definitely need to do something about it, because at the moment it's a little bit messy, I guess. So it's something worth noting and maybe putting on our to-do list at some point. So uh, let's see, what do we need to dig into today to get stuff moving along? For now, we will just keep this possible UI rebuild in mind, and then we'll work a little more on the custom text dialog and the font stuff. So one thing that we definitely need to do is to come up with some code that will either convert this glyph atlas into usable code, usable data, and then build some kind of text rendering and see if we can come up with some kind of shading routine that can do the shadow shading of the colors just like the originals are here, and then go from there, I guess. So let's see if we can get some of that stuff done. Now, I did extract all of the assets from the game client that we're currently using. That, by the way, is the default icon for our resource pack. In the textures section, we've got the font folder, which contains the ASCII default setup. There's one here with all of the enchanting symbols, and the rest of them are Unicode images for all the different glyphs. So a quick glance at this image tells us that it's 128 by 128 pixels. There are 16 glyphs per line and 16 lines in total. So 128 divided by 16 makes 8, which means each glyph is 8 by 8 pixels. So we definitely need to account for that when scanning this. I shouldn't have closed that down. Let's grab it again quick. This one. So when we scan the original to basically convert it into some kind of data that we can use, we kind of need to be aware of the actual glyph size, so we can correctly grab the data that's needed. In the original PNG, a transparent pixel indicates, of course, transparency, and a white pixel indicates that something should be drawn there. The game client makes use of some kind of color shading to basically show the glyphs in whatever color the chat element describes. Since we don't exactly have that option available to us, we'll build a looking for the words here. We'll build a binary setup of each individual glyph, and then use that to determine what to actually render into the image when we draw a string. Okay, that was kind of weird. Lost connection on my headset there. Um, all right. Um, let's see. We definitely. Oh, I didn't want to close that down. We definitely need something that can convert this into usable data. Um, so let's see if we can start by constructing that, and then we'll figure out the other stuff afterwards. Um, there are options available for us to do things like bold text, as we saw in the other example um, right here. Um, and there are also options available for doing italic and underlined and strike through and such. For the moment, we have not implemented those as part of the chat converter. However, it is expandable, so we can add that in. Um, so it shouldn't be all that huge of an issue for us later on adding those features as well. Um, all right. So uh, let's see if we can get some of this stuff done. Let's see, we don't really have a good spot to put this. Um, da, 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 da. Meh. We'll do, yeah, we'll just put it in here. Um, add in a class. We need some kind of handler for this. And we also need to figure out exactly how we are going to output this rendered text. We could potentially set this new class up to simply just return a bitmap containing basically the rendered text as a finished image that we can then draw. Or we could return some kind of bit pattern and then let whatever on the outside handle how this bit pattern should be handled. I think I'm going to go with the fetch a bitmap so we can basically draw it straight onto the main form as needed. Or whichever other form needs this particular text rendered. In any case, we definitely need something that can handle this. So we'll call this Minecraft font. And then do some stuff with this one. Stuff in a constructor for it. And since we at least need to, at some point, do some image to data conversion, we do have the option of adding said image, say the default ASCII font. We can add that as an image resource to the project. And then simply grab it from there and do the conversion so we can do the faster rendering of the font glyphs as needed. Or we could import them as a separate method, do the conversion, and store the converted data somewhere. I think I'm just going to go with importing the original image as a resource and then do the conversion of that glyph image into usable data whenever we build this up. So um, that way we don't have to rely on other resources that we might end up not being able to reference. We can get rid of test code, and we don't particularly need to do any additional resource handling as such. So let's actually start by adding that default font. No, that would be in the game client, assets, Minecraft, textures, and the font. So we'll grab a copy of this one and then put it in the resources. That would be this would contain the icons that we have on the UI, and here we will put font glyphs, stuff that in here. Let's see, we might want to rename this font glyph ASCII. There we go. All right, and then we will add that into our project resources. Right here, existing file, stream projects, and fetch this one, font glyphs ASCII. There we go. All right, now we've added that in there, and I do believe that we already have a method available in the main form to fetch these image resources. Let's see, get resource bitmap by name. We've got that right there. So when we build up the Minecraft font stuff, we'll simply pass the font glyphs ASCII bitmap to the font object, and then let it do some conversion internally so we can speed up the process. So part of building up a font rendering or a text rendering scenario setup. If we grab a quick look at this one again, there we go. As you can see, the major difference between what's actually in the font glyph chart, sheet, atlas, whatever you want to call it. Here, each individual letter actually does take up the entire 8 by 8 pixels as defined by the PNG size, which means the image itself is basically just a glyph atlas, where each of them is a basically defined as a monospace setup, meaning that all glyphs are of the identical size. However, when the game client renders them, they are rendered as a non-monospace font. So in doing our conversion, we kind of need to measure out the size of each glyph so we can correctly put up the spacing. As we can see, the game client renders out 1 pixel spacing between each letter, which also holds true for the chat, in-game chat. As we can see here, these do not have any kind of shadow effect on them. So our text rendering routine needs to be able to render the text with and without the actual shadow stuff that the client game client does in chat. So we need to keep that in mind when we build it. Since we will be doing a lot of pixel drawing on an image to properly add in these glyphs, we kind of need to come up with a way of doing this that's sufficiently fast. And using the bitmaps set pixel is definitely not the way to go. It is way too slow. Anyone that has ever tried reading or scanning an entire image for pixel colors using getPixel knows exactly what I mean. It simply just takes way too long to go through that entire process and end up with some kind of, I don't know, color list or whatever's being done. Too slow. So one of the amazing things that we can actually do is that we can basically grab a snapshot of the bitmap's memory buffer, which contains raw pixel data, and then we can use that information to figure out exactly what's in the image. Now, for the font itself, it's fairly straightforward. Granted, this one is an edited version of it, which is doubled up. But basically, the premise is that if there is a transparent pixel, it needs to be transparent, and if there is a solid pixel, it needs to be drawn in one of the 16 colors, depending on what the chat element says. So that's the basic premise of it, and with that information, we can easily grab the raw data from here and the raw image and convert it into some kind of useful data, which we are going to have a look at doing right about now. Public methods. I like to set things up this way so I can keep track of what goes where and why it's in there and so on. So here we will add one called set glyph bitmap, which would be basically the method that overall initiates the data conversion from image to raw data that we can use. And then we'll do a bitmap here, glyph bitmap, and yes, I know, complaint, grab that one. So we can properly, there we go. All right, so the reason we're putting a glyph bitmap as the argument here is because we embedded the default ASCII font glyph sheet similar to this one. We embedded that as a resource within the project itself. Hey Joban, good to see you. By doing this, we can grab the resource from the assemblies and stuff it into this class, and then have it internally handle all the stuff that needs to be done with it. We know that we're going to need some way of storing this glyph data. And we also know that each glyph sheet is basically of the same size, more or less. I know that some of them might be of different sizes because of the Asian symbols, some of them are a little bit bigger than the 8 by 8 that can fit in here. So some of those Unicode sheets might be 256 by 256 instead of 128 by 128. So in this particular setup, we definitely need to keep track of what the original glyph bitmap dimensions are, so we can correctly rescale the font setup for it. Now, as part of that stored data, we need to know the actual glyph size, as well as in doing the scanning process, we need to figure out exactly how wide each individual glyph is, and we need to be able to potentially shift or offset or move that's pretty annoying. My headset keeps turning off because it believes that nothing's going on. Bear with me just a second. Um, let's see if this fixes the issue. Okay, that was majorly annoying. Anyway, um, yeah, we need to store the glyph itself. In case a glyph is, how should I put this, not correctly aligned, we need to be able to basically shift the glyph data to the left or to the right, depending how we choose to end up drawing this stuff. And in doing so, we also need to store some kind of information that tells us exactly how wide each individual glyph is. The reason we need that information is so that we can correctly measure up what kind of width is required to render this particular string that's being passed to our font object. So there's a bit of data that we definitely need to keep track of. And we'll see if we can work out a way to store this stuff. Now, we know that we need to work with it. And we know that we need to work with or be able to render an entire font setup fairly quickly. So doing a lot of data compression and data expansion when doing this stuff is probably not the best idea, since we need speed for this. So instead of using a bunch of booleans to basically determine whether we need to draw a pixel or whether we need to ignore drawing it, my immediate idea is to simply just grab an array of bytes that make up the glyph, and effectively store each individual glyph as byte information, where a byte of 0 is transparent and a byte that's non-zero needs to be drawn. We also need to declare a list of the different colors so that we can draw them up correctly, and we'll need to implement that as well. For that purpose, I'm going to go grab the let's see, we need the color reference, Minecraft chat colors, formatting codes on the official wiki. There we go. And this thing is just being slow as usual. these are the ones we need. Um, all right. So this list of colors we definitely need to implement somehow. In doing so, we could do a pre-initialization of the individual shades for drawing shadows on the characters. Um, but for now, let's get some glyph scanning code built so we can do the font data building, or sorry, font glyph setups. For that, we are going to need some measure of storage. We know that we always get 256 glyphs within each chart. Whether each individual glyph is actually drawn or not kind of depends on the image itself, but we'll assume that we always get 256 glyphs. To store each individual glyph, we need some kind of bit reference with an added width and added information about the actual width of this particular glyph. So we'll add in, I don't know, we'll just call it glyph for now. We need the width of each individual glyph. Hi, Apollo Bean. Good to see you again. So we'll add in the width, and since all of these glyphs are always of the same height, we don't exactly need to store each individual glyph height, so we can skip that. But we do need a byte array containing the basically the bit reference for how to draw this particular glyph. So we'll call this bits. That should be fine. And then to store the entire glyph sheet, we'll add in another struct and call this glyph sheet. And this will need to store the actual or the full width and the full height of each unique glyph to kind of indicate to us what is the potential maximum size that we can end up spending drawing each individual glyph. So we'll just make those byte since these particular glyphs won't ever become all that huge. We can easily use a byte for this. I doubt that we will end up having glyphs that are bigger than 256 pixels each. There we go. And then, of course, we need an array of glyph from above. So we'll add that in as well. And we'll add that as glyphs. There we go. And of course, we need to do some initializers and whatnot for these. All right, so this is the monospace width of the glyphs in the font. This is the monospace height of the glyphs in the font. List of all glyphs. There we go. Actual width of this specific glyph. List of bits that determine whether a pixel should be drawn or not. There we go. All right. So, how are we going to get this stuff working? Potentially we could actually just turn this into, say, specific. Yeah, we might as well actually do that. There's really no need to stuff that into another struct, since we don't need, at the moment, we don't need to be able to load multiple different glyph sheets. Really no point in doing this actually. One thing that we do need to know, or do need to add in, is a scanning method that will take the glyph sheet bitmap and convert it into this data instead. All right, let's get rid of this actually, and then I'll just add them in here. We set a byte for, well, yeah, we'll call these glyph width, and do another one for the glyph height, and then we'll do a array for these, and we'll just call this glyphs for now. There we go. All right. The scanning method. Now we can either do that here or do it in a separate one. I think I'm going to do most of the scanning stuff down here. However, since we don't exactly know what kind of pixel format the glyph bitmap will have, we kind of want to see if we can do either a check on that or a straight up conversion right away. We know that the original ones always show up in white, but then again we really don't know whether Mojang at some point decides to change that, so that could become a problem. But if we take a quick look at the properties for the PNG, we can see that it actually says it's a 32-bit image, which means we do have an alpha channel available, so we can go through that. But just to make sure that we actually end up getting a 32-bit setup, we can do a quick conversion of it. For now, let's just let's just leave it at that. We'll do a quick check if this has a pixel format that equals to one of these. We actually don't know if it could assume some other setup. I know from experience that a 32-bit PNG always reports as the format 32 bits per pixel ARGB format, so not a huge issue. And it'll report exactly the same when you grab such a PNG and embed it as a bitmap resource within the project itself. So we know that. We can use this. I know that assumption is the mother of all screw-ups, and at some point we may want to change this up to be less assuming, I guess. All right, so to scan this, I think the fastest way of achieving such a scan is by grabbing this particular bitmap and effectively converting it into a byte array, and then simply just move a positional index pointer within. Um, yeah, I could put an assert in it. Um, doesn't really matter. Um, in any case, we'll do a quick conversion. Now, um, to do this, we need to set up a buffer, and that needs to be a byte array. So this would be the uh, new byte. And this buffer of bytes needs to be able to fit all of the raw data that makes up the glyph bitmap within it. So to accomplish this, we need to initialize the buffer at a sufficient size, which would be the glyph bitmap width times the glyph bitmap height, width gange height, or times height, sorry, equals the actual pixel count within the image. And since we are using a 32-bit image, that means we need 4 bytes per pixel to correctly define each individual pixel's color and transparency. So we need to bump that up by 4. All right. Next up, we'll make use of a little bit of memory copying to grab the raw data from the bitmap object and convert it into our buffer. All right, so to do that, we need to reference bitmap data, which at the moment we don't have a reference to because it's in the system drawing imaging namespace. So we'll grab that. I'll just call it data. And then we will lock all the bits of this particular bitmap that prevents anyone else from messing with the contents of this particular bitmap while we're doing these operations. Yes, basically it's to build up something that would be able to eventually do something similar to this. The reason I chose to go down this route is so we can approximate what it would look like as part of the future custom text editing dialog. So we can put in bold text and all the rainbow colored text stuff, and basically get, at least for the MOTD, do some customization and do it in a way where it's a little easier than sitting there basically pulling your hair out trying to get it working, because the only way that you can figure out whether it works is to, let's put it this way, start up the server, try and go on the multiplayer listing, and then see it from there. Well, I could use a true type font that resembles the Minecraft font, but anyone that has ever messed with manual font rendering knows that when you do a measure string on the graphics or through the graphics object, measure string always adds in some padding at the beginning of the text as well as at the end of the text, and you cannot get rid of that padding. which means you would effectively end up getting slightly offset text rendering when you do multicolor changes, like for example here, the apple in Applecraft is dark red, dark red, bright red, dark red. Same for the craft. And if you attempt to do some cross calculation of this, yeah, you can do it with the Win32 API stuff, but that's a little. It's one of those hacks that I would probably do in a similar setup. But a lot of people kind of run away scared whenever you start embedding things like direct Win32 API calls. And I kind of wanted people to be able to still follow what's happening here. So I chose to go down this route instead. In any case, copy over this the raw data from the bitmap to our buffer. That's what we were doing. Okay, so we need to tell the logbits method the area that we want to manipulate. And we do this by adding a rectangle that basically has the size of the glyph bitmap, the height. Then we need to tell it which locking mode. For this, we need to lock the bits for reading because we just want to read from it. So we'll choose read only. And we need to tell it what kind of pixel format we expect. Since we already know that this particular image is in the ARGB 32-bit setup, we can simply just specify the glyph bitmap and its pixel format. I'll break this up a little bit so it's easier to read. And just for making this a little easier, using, oh, it's already in there, sorry. There we go. All right. Whoops. Create a buffer that can hold the entire bitmap. Width times height times 4. The 4 above 32 bits, which is not that one, I wanted this one. 8 bits per channel, 4 channels equals 32 bits. Simple. Lock down the bitmap for the memory copy process. And there we go. Get these down here so we can actually read them. Define the area of the bitmap we wish to manipulate. There we go. We only want to read pixels, and this is the format it's stored in. All right, so the bitmap data object is used to let us basically dig into the Windows Memory Manager and grab stuff by making use of the system interrupt services. That way we can basically do an array copy from active memory into a variable. and back again if needed. Um, Anyone that's ever done any kind of C or C++ knows exactly what this is, because every kind of variable handling and most kind of data swapping around in C and C++ is basically messing about with more or less active memory all the time. So this is somewhat familiar. Though in managed C Sharp, we don't always have direct access to active memory. So this is one of the ways that we can actually do that. And yes, even though this may seem like a bloated way of doing things, there is fact to back up the speed difference in terms of processing each individual pixel within a bitmap like this. If you do this memory copy over and then process the byte array afterwards, it is by a long shot way faster than using the get pixel and set pixel methods of the actual bitmap object itself. This is the fastest way of processing it. Um, Granted, these pictures are not or images are not particularly big, but any kind of speed increase that we can get from this is definitely preferable than this ending up being, I don't know, a turtle with arthritis going uphill in stormy weather. So we'll take the fast approach. Thank you. We'll use the Marshall method from the system runtime interrupt services and copy. All right, so here we get a list of 16 different ways that we can actually do stuff right here. The first one that it suggests accepts a byte array, an index position at which to start, a destination pointer, and a length. At the moment, we need to move stuff from the bitmap to the buffer. So we need one of these methods that starts with a source pointer and a byte array as a destination setup. So let's go through these and see what we can find. See, here's one we can use. We've got a source pointer and a destination byte array, a start index within the destination byte array, and an expected length. So the bitmap data has a property called scan0. That is the pointer to where the very first pixel is within the bitmap's active memory. So we'll specify that as the source pointer, and then we'll reference our raster image byte array above. We need to start at the very beginning of it, and since we already pre-calculated the size when we initialized the buffer array, we can simply just specify the length of it, and we're done. Now, the next part of this, and this part is very important, is that we need to unlock again. Basically, release the hold that we currently have on the active memory of this particular bitmap object. It's very important to remember. If you don't, you could end up basically creating reserved bits of memory that could at times end up doing some weird things on your computer. So do remember to release it. The way to go about that is to call the unlock bits and then basically just pass the original bitmap data object, which is called data, and that's it. bitmap data doesn't contain a dispose method, so we'll simply just terminate it. There we go. Get rid of it. We don't need it anymore. All done. All right. So now we've got our buffer filled up with all of the original data from this particular bitmap, and that lets us scan through it. The one thing that we at the moment don't exactly know is in which order each of the four channels that determine the pixel color and transparency. We don't know the actual order of them, and yet we actually do know it. Yeah, I know it's kind of confusing. See, usually when you set up a color in the system drawing space, namespace, you can do something like this, and you say from ARGB. And if you flip through these, you will see that it expects the alpha channel, followed by the red, followed by the green, and finishing off with the blue channel. So basically, it's A, R, nope. I'm trying to cheat it here. G and B, like this, right? Now, when we Marshall copy like this, the order of these four channels is simply reversed, which means the first byte in the first pixel will be the blue channel, followed by the green channel, followed by the red channel, finishing off with the alpha channel. So we just need to keep in mind that the channels are reversed. And if memory serves, this reverse order is also the exact same order that graphics cards accept texture definitions. So if you were to send a texture to a graphics card, say through DirectX or OpenGL, the raw data would be in the exact same format. I stand corrected if I'm incorrect on this, but I do believe that's the case. Okay, moving on. We are building all of these individual glyphs. Just to recap quickly, these are the ones that we're messing with. So to begin with, we definitely need to set something up that can scan these individually. And from there, we need to do a setup that can accept the raw data in, and then store it so we can more easily cross-reference these. The reason we need to scan them individually is because we kind of need to slice up this entire image in the correct size. So since we already have at least some measure of information available to us in terms of how many glyphs are in there, we can calculate the actual glyph width and height fairly easily, because we have the glyph bitmap width and height, and we know that the image itself follows 16 by 16 characters, so it's completely square. So to define our glyph width, we probably need to cast this as a byte, because calculations take place as integers and floats and whatnot. In any case, the glyph bitmap width divided by 16, cast it into a byte because that's what we declared it as. And the same thing goes for the glyph height. Right, like this, and the height here. There we go. 16 glyphs per line. 16 lines of glyphs. There we go. Fairly straightforward. Now with this, we don't really care how big each individual glyph actually is. We just need to know the size of each individual glyph, and that's it. From here, we need, excuse me, we need to loop through and then check the setup in our buffer to figure out exactly which pixels contain some useful data and which ones are transparent. So, since we know the 16 by 16 glyph setup, we'll just loop through that. So, let's see, we'll go y by x. So this would be the line L less than 16, and we'll need to do a row less than 16, and then inside each of these we need to do a glyph width by glyph height scanning process, so we can correctly declare each individual bit setup. So at the moment we only have these references. We still need to set up our buffer or our glyph storage, so we'll do that. Let's start by killing off the if for some reason we are replacing an already set glyph bitmap with a different one, we kind of need a method for killing off the old one. So let's do a method for that. Let's see. Just blah 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 blah. Let's call this. Nah, reset isn't particularly good. Let's see. We'll call this dispose all glyphs. Yeah, that works. There we go. Let's do a void for that, and then have this one go through and kill all of it. Alright, so if this array is greater than 0, then we'll loop through and delete all of them. I know that technically speaking this isn't required, because you can simply just set it to a clear like this, and the memory manager of .NET will internally figure out to recycle the memory for it. Well, we'll do this anyway. There we go. This needs to be like this. Kill off any pre-existing glyphs. There we go. All right. So we definitely need to get rid of any potentially existing glyphs before we start putting stuff in here. All right. So to index all this stuff, so we can draw or put the individual glyph data in its correct slot. We need some kind of indexer that can correctly, excuse me, index the current glyph that we are working with. We could just do the calculation stuff. We can do it counter. Doesn't really matter which one we do. We'll just do a counter for now. Call this glyph index. We'll start at 0 because that's the first one we need to reference. And after processing the data for this particular glyph, we then need to increment the glyph index, so next time it'll point to the next slot in our glyph setup. So do that. Here we need to pixel scan each glyph. Okay, so we've got the width of each individual glyph, and we've got the height. So first we need to initialize the bits array of the glyph that we are about to create. So we'll do that. Glyphs initialize as sufficient buffer to store the glyph bits. So since we have the glyphs array right here, and we can reference it by glyph index, and it's got the bits byte array, we'll set this up. And this one always needs to be the size of glyph width times glyph height. So I'll do the glyph width times the glyph height. There we go. Now we've got sufficient storage space to put it in there, and then we'll loop through the individual pixels within our bitmap buffer. Now, when we calculate where each individual pixel is within the image buffer, we need to remember that each pixel within our buffer takes up 4 bytes. So we need to make sure that we correctly calculate the position within our image buffer. Let's see, for this we need the height less than glyph height right there. And of course we also need to loop through the width of it, which would be right there. There we go. Alright, so this is supposed to end up with us being able to reference each individual pixel within each individual glyph. And we of course need to do quite a bit of math to get all of these positions calculated correctly. The first one is pretty simple. The result needs to end up with 0. The second one needs to end up being 4, and so on and so forth. All right. Excuse me. Okay. Let's see. We've got the line, the row, the height, and the width. So let's see if we can work out whether this particular pixel is the one that we need. Just for reference, let's see, I'll put this in byte order of the pixel color channels. Image 0 is then the blue channel. This would be the green channel, and this would be the red channel, and this would be the alpha channel. There we go. Now we've got that information so we can correctly reference it. Okay, so whenever we calculate a pixel start position, we need to add another 3 to that position to get the alpha channel, because we're simply just going to check whether the alpha channel is, say, greater than half strength or less than. If it's less than, then we'll assume it has to be transparent. If it's greater than, then we'll assume that it has to be solid. All right, so to calculate this, we definitely need to go through all of this stuff. We know that we've already calculated the width and height of each individual glyph, as done by dividing the width and height by 16, because we have 16 glyphs per sheet. 16 glyphs per line and 16 lines total. Let's get we'll just do this for referencing at the moment, and then we'll do all of the calculation stuff in here. All right, so since we also know that each individual pixel in our raster image buffer takes up 4 bytes, that means for every one of line, we need to at least calculate the entire width of a single line. Let's start by adding that in here. Each line is made up of 16 glyphs, and each glyph is made up of glyph width, and we need to do times 4 because it takes up 4 bytes per color channel. So this should be sufficient to calculate the total width of a single glyph line. And on top of that, we need to add the current row, which is a similar calculation. The row times 16, because we have again 16 per line, and again the let's see, the glyph height times 4. There we go. Now we've got these, and on top of this we also need to add in specific positions for which of these actual pixel references we need right here. This is where I usually mess up in the math. So if you spot a mistake, feel free to tell me I'm a derp. All right. Let's see. Since the actual height of an individual glyph determines the basically the Y position within our buffer, we kind of need to at least know how wide each line of pixels actually is. So it might be more beneficial if we do that calculation once and then simply just reference that, so we don't have to do all those expensive calculations every time. Um, so let's see if we can do um, a setup for that. Let's see. Um, line width. Um, let's call this pixel line width. That's probably better. All right, so this one would then be basically the glyph bitmap width times 4. That would then correctly account for an entire line of pixels. And since moving down is basically just incrementing by the total pixel line width every time, it would be a little easier doing that calculation here. So glyph bitmap width times 4. So that would grant us um, the total width of a single line of pixels. All right, let's get rid of this stuff quick. Okay, so here we need to figure out exactly which line of glyphs we're starting at. So that basically becomes the pixel line width times the um, let's see, glyph height. Um, so the line would be times pixel line width, and that would then be times the actual glyph height. So let's grab that. There we go. That's a little easier to keep track of. Plus the row position, but this is then an X position, so here we need to grab the glyph width times 4, because each pixel within the glyph itself takes up 4 bytes for the 4 channels. So plus, that would then be the row, whoops, times the glyph width times 4. Alright, so this should now put us in the correct position for the first pixel within a single glyph, as determined by the line and row loops. Alright, so here we need to add these extra offsets for the glyph height and the glyph width. So again, here we end up with something that moves the position on the y-axis. So here we definitely need to grab the current height times the pixel line width to correctly move it to the next y position. There we go. And then we need to add in the current x position, which of course becomes the w times 4, because each pixel takes up 4 channels. So that's basically it. And finally, we need to move to the alpha channel offset, which means we need to add another 3. There we go. So this should now grant us a byte information that tells us the strength of the alpha channel for this particular one pixel of the image buffer. All right, so far so good. If we assume that an alpha value of less than, say, 128 needs to be transparent, and anything above that needs to be solid, we should be fine. So here we need to, let's see, where is it? Where is it? There it is. All right. This is the one that we need to mess with. So put that down here quick. All right. So if A is greater than, say, 127, solid, and transparent, right? So if it's solid, we'll simply set the bit to 1, and if it's transparent, we'll set it to 0. So to correctly reference this, we need to use the H as well as the W variables to calculate the position we need to put this bit into. So at the moment, that would be the H times the glyph width, because that's the width of each pixel line. Glyph width, like this, plus whatever the W is at the moment, to account for the X position within this bit list. And we'll set that to 1. And this, of course, is identical for a transparent, except the value is different. 0 indicates transparent. 1 indicates solid. There we go. And the glyph index is being updated down here, so this should take care of scanning these glyphs correctly, if I've done my math correctly. And that could be a big if. I always mess these up, and sometimes it takes a couple of run-throughs before I get it right. For whatever reason, I just cannot retain that kind of math information from time to time when I use it. Must be my age. In any case, this should take care of scanning those bits for us. So when we're done doing all this, oh, actually, there is a crash bug in here because I didn't initialize the glyphs array to accommodate all the glyphs that we're going to put in here. So we'll do that down here. Glyphs equals new glyph, and this would then be of course 256 because we've got 16 by 16, so we'll just do 256 right away. There we go. Okay. Now there is one more thing that we actually need to do to complete this, and that's basically to check each glyph being constructed to see what the actual width of this particular glyph is. Now we can go about this in one of two ways. Depending how we want to define the actual width of a glyph. So if we grab a look at these quick, as you can see, the small or lowercase l right here basically takes up 2 pixels. So the correct width for that L would be 2. because that then indicates the exact amount of solid pixels in the width of this particular glyph. Um, the alternative way would be to build in the letter spacing um, as part of the actual glyph width, in which case we need to add one for transparency or one transparent pixel, in which case the glyph width becomes 3. Now, if we put that spacing in as part of each individual glyph definition, then that basically ends up working against us a little bit because we wouldn't be able to, say, on the run change the character spacing when rendering the text. So for this setup, we will calculate the actual number of solid pixels within each glyph on the width, and then we'll let the actual rendering routine handle the letter spacing. That way we can simply add in a property on the class itself that lets us specify what the spacing should be, and then let the renderer handle it. Of course, if we do it this way, then we also need to update our calculation routines to account for this kind of default letter spacing and whatever letter spacing we might end up making changes to. So it's something that gives us a greater degree of freedom. We do have one tiny issue at the moment. And that issue is actually that we have 3 glyphs within this current sheet that are basically empty. The very first glyph is empty. There are no pixels within it. The spacebar, white space character doesn't contain any pixels, so for this we need to kind of hard code what that particular spacing should be. And again, the very last glyph down here is also empty. So again, we end up having something that we need to handle somehow. At the moment, if we simply just scan for solid pixels within a glyph to calculate its actual width, then these 3 glyphs will basically end up having a width of 0. That's not particularly good when it comes to the white space. So for that one character, we definitely need to figure out exactly how many pixels that single one glyph needs to have as a hardwired spacing or width, sorry. So let's see if we can perhaps maybe figure that out. Let's see, graphics, UI samples. Let's see if we can guesstimate how big that thing should be. Okay, so here we have a couple of examples of some spacing here. It kind of looks about the same. We know that there is a forced 1 pixel spacing between each letter, as we can very clearly see. So whatever count we end up getting between these two should be subtracted by 1, so we can account for that forced 1 pixel spacing between them, and thereby let us calculate what the actual spacing is. Now, in this particular situation down here, it is actually fairly easy for us to see, because the background here um, gets us basically the information we need. See, this, I'm not sure how visible it is on stream, but this bright brown here is actually 2 by 2 pixels. Um, and the same goes for the brown one, dark brown one down here. So we have some measure of being able to count these up. Now, for this, we need to keep in mind that it's already doubled up. Um, Basically, these pixel sizes match each other. So the one pixel sitting right here on the one is a singular pixel. And since these basically make up 2 by 2 pixels, we can very quickly calculate that this makes up 4, 6, and 7, which equals the glyph itself. So to figure out the actual width of the white space character, um, this quick screenshot actually tells us. This square is 2 by 2 pixels, this one is 2 by 2, so that's a total of 4, which means our white space width needs to be hardwired to be 4 pixels. Now, of course, we can also put that in as a separate property, which would then allow us to change the default white space width, should we want to. It's an option that is available to us. But these are some of the things that we need to keep in mind. All right, so let's see if we can get we need to build some code that can scan these bits after constructing the glyph in our list, and then work out exactly how wide this particular glyph is. In doing that scan, we also need to tell that particular scanner which glyph we are currently working with, and if it's the white space character, which is character 32, then it can basically ignore doing the scan and hard code it to become 4 pixels in size. So that part shouldn't be all that huge of an issue doing. Let's see if we can stuff in some internal helper methods. So here we will do a method called scan glyph width. And for this, we can either specify the glyph itself or just pass the array and then update it down here. Let's see if we can we'll do a reference to the individual glyph itself, glyph, and then we also need to specify the glyph index. There we go. All right. So what can we do with this? First of all, let's see if we actually have to scan through it. So if the glyph index here is 32, then we're not going to bother scanning it because we know for a fact that it always contains a white space. White space equals nothing drawn. So this is nothing more than just basically an empty setup. So here we'll set the width of this particular glyph to 4 pixels. There we go. And if it's any other glyph index, then we'll actually go through and scan it. Now, um, we already know that these two beautiful variables up here already tell us the width and height of any individual glyph. Those would be the maximums. So we can use those to properly work out the actual width of each individual glyph. Actually, we don't need this because we don't have to calculate the start position of it. We can assume that it's always there. So we'll just do, we'll start by doing setting the width of it to 0. And then we'll loop through the size of it and check it out to see if we can find any solid ones. So that's fairly straightforward. I'll do a y less than, that would then be the glyph height. And of course the x axis as well, which would be the glyph width, x, there we go. And then we need to look for a solid bit, which if the glyph.bits, and in this case it's the y position times the glyph width plus the x position. If this is greater than 0, and the current width of the glyph is less than the x position plus 1, because we're counting a width, not a position, then we'll update it. If the glyph.width is less than x plus 1, then update the width of the glyph to become x plus 1. There we go. And this, of course, needs to be cast as a byte because it's a byte value. There we go. All right, so in doing this, I'll grab this quick. What happens here is that basically it loops through all the individual pixels or bits of this particular glyph, looking for one that's configured as a solid one. And if it finds a solid one and that the position, the x position of that particular solid pixel is greater than, actually the k is a little better to use, is greater than what was previously stored, as this would be the case for the topmost pixel on the k here, then it'll update the width. But since we are going through the bit grid as positions, we need to add 1 to the position to get the actual width count. If we just added the position, it would get a width of 3 pixels because we're counting 0, 1, 2, 3, and so on, whereas it actually needs to have a an actual width of 4 pixels to accommodate all 4 correctly. So there we go. This takes care of scanning the actual glyph width of it, and correctly updating it internally. And once this is done, we should be fine. So let's remember to get that scan done. Scan glyph width. We need to pass the current glyph index as well as the glyph index. There we go. Okay, so what's this weird ref that I put in here? Um, and why did I put that in here? Um, when you create methods with arguments, you have different ways of passing data back and forth between methods. By default, whenever you specify something without some type of um, how should I put this, directional keyword, you effectively send a copy of that data to the method that you are placing the call for, which would be the case for glyph index. Basically what that means is that up here in the scan glyph width, this glyph index is basically a new variable being declared containing a copy of what was specified. So we could potentially change the contents of the glyph index within this method without it affecting the other one. Um, by specifying an argument using the ref keyword, you are telling it to only pass a reference to it, which is similar to what a pointer is. So basically, in doing this, I'm telling scan glyph width to use this specific variable and update this specific variable. Um, so it points to um, um, this particular variable instead of creating a new instance of that variable. So that allows us basically bidirectional data in and out by means of an argument. I know that there are tons of better explanations on how this actually works. Um, I'm lacking the words for it today. I've had a pretty busy week, so I'm a little bit out of my element today, I guess. I do apologize for that. In any case, in a similar fashion, you can do in and you can do out as well as ref, and they then determine which direction the data goes instead of just creating a new copied variable instance of whatever it is you're passing. When it comes to discrete variables like these, sometimes it can be a benefit, sometimes it can be an annoyance. When you start passing objects around with child objects and lists in them, you may want to consider how you're actually passing those as arguments. In some cases you need to update them, in some cases you need to definitely not update them, and so on. So these need to be chosen with some amount of care. Um, Alternatively, I could have done this updating as a setup like this, for example. This is not going to work. Then I'll just grab this like so. And I could have done this. Right now it's complaining that the second argument isn't passed with the ref keyword. I could have done this as well. The quick and easy way of solving the issue of updating the width within this glyphs array, well, it's just so much easier and quicker to just pass a reference to it, which is basically a pointer to this particular variable, instead of us creating a copy that we then have to return. So that's what it is. All right, so in doing this, we basically just get a different variable name, but it's still the same variable that we are updating. For the glyph index, it doesn't really matter whether we grab a copy of it or reference the original one. for a purpose like this, I prefer having the copy because if by some chance I end up doing something stupid within this method that potentially could update glyph index, then at least it won't affect the other method. So, but here we actually do need to update the width. So having it passed as reference, as a reference, just makes life so much easier. There we go. So that should take care of calculating or scanning, checking the actual width of each individual glyph. Excuse me. Um, by simply counting up how many solid bits have been set along the x-axis. So fairly straightforward, nothing too major about that. And that should take care of the entire glyph setup. Okay, let's go through this quick again. We've set the maximum, I guess, glyph width and glyph height as defined by the glyph sheet. We've gone through and scanned each individual pixel within the original glyph sheet image and converted them into a bit list, basically. The reason I chose to put it as a byte array is because typically a byte is only 1 byte big, but depending on architecture you're compiling the code for, a boolean, which is a bit true and false, can basically spend anywhere from 1 byte up to something like 8 bytes of memory just to hold a true-false value. So by checking a numeric byte value instead, it's the same thing. We're just certain that we take up only the amount of bytes that we actually need to store the information needed. All right, let's see. Kill off those. The last thing that I want to do after completing the pixel scan is to trash our image buffer. I know that technically speaking, the garbage collector will come do that for me after we're done with the method. But I like to clean up after myself. Old habit. So I'll simply just kill it, set the length of it to 0, and thereby instructing the garbage collector that the buffer that we previously had assigned, you're free to clean up now. Kill off the image buffer. We're done. There we go. All right. So what have we accomplished so far? We've accomplished grabbing an image similar to this and converting it into some raw bit data that we can then use to build up a rendering routine to hopefully be able to accomplish something along the lines of this stuff. At some point, if we do decide to say add in things like bold support, italic support, we will definitely need to have a look at how the rendering routine works because in this screenshot we can already see one major difference, or a couple. When it draws the text as bold, it basically widens each glyph by another pixel. So that's something we need to account for, as well as account for in space requirements or text width calculations, so we can calculate the correct width of it. Just something we need to keep in mind. It's not vitally important now, but when if and when we add support for that, we need to account for that as well. All right. We are coming up on, let's see, yeah, let's grab a quick break for nature call, fresh coffee fetching, smoke 'em if you got 'em kind of thing. And then we'll crack on with some rendering stuff and a little bit more math, and we'll see what happens. And yeah, see you after the break. Be right back.